I'm paid by Simon Fraser University. I'm in a School of Interactive Arts and Technology and a Cognitive Science program. I'm also affiliated with the University of BC, in the Media Graphics Interdisciplinary Center. This year I'm on sabbatical as a visiting scholar at University of California, San Diego at the Cal IT2. And I'm part of the leadership board of Vaccine, which you heard a lot about from Dave Ebert. I'm not going to talk much about vaccine research today because you've already got it from Dave. I will talk a little bit at the end. What I'm going to try to do on my first half of my talk is to give a bit of a theoretical background, how we approach visual analytics from a cognitive science perspective, and then I'll give some concrete examples in the afternoon. So I think in the spirit of the last talk, there's nothing new under the sun. The visual analytics concept, I think, can be taken back to Doug Engelbart, as so much of computing can. This idea that there's a human capability that can be augmented, and that we can build a system, and a system is not a technological system alone, it is the technology, the trained human, and the organization in which they operate, and through that we can augment human cognitive performance. So there was a lovely paper in 1965 that Doug wrote that really set a lot of this off. And so we did almost nothing about that until the mid-2000s, which is a long time. And I personally think that the origins of visual analytics can be traced back to a paper by Bill Lawrenson. If anyone is familiar with computer graphics, Bill Lawrenson has the most cited paper in computer graphics, the Marching Cubes paper. So he's a famous computer graphics guy, but he works for General Electric. And so he's got an industry side. And he wrote a position paper for a conference in Washington that involved the funding agency, so it was something that was interesting. On the death of visualization, can it survive without customers? And it was sort of j'accuse for the visualization field. Visualization alone is not a solution, but it is a critical part of many applications. The community of visualizations lacks application domain knowledge. So visualization has become a commodity. No one talks to the people in VisWeek. They just go and use Tableau. And it's not having an impact. You don't see parallel coordinates in your Excel spreadsheets. One might argue that that's a good thing. But we're not really getting our work into real-world applications. So this is a fellow who's working in industry and realizes that we're not having the impact we should. The visual analytics movement started, and I think maybe in part as a response to that, and Jim Thomas, of course, is the father of visual analytics, if we can say that. And after 9/11, the DHS brought a number of people together for a panel, and they met with people from government. At that point, it was heavily geared towards investigative analysis to try to decide whether they could make the visualization actually work. And I was part of the group that wrote the research agenda, Illuminating the Path. It was an interesting experience. When I began, I'm used to being brought into technology projects to bless the product before it goes out in grand HCI tradition, or to give them some design guidelines up front. And I thought this would be a similar kind of project, but in fact, they were really interested in the cognitive science. So much so that there's 2 chapters of the book that could arguably be called cognitive based. And one of the quotes is that we need a science. Visual analytics is defined as a science of analytical reasoning, and I think people understand what a science is. We'll talk a little bit about that. That is facilitated by interactive visual interfaces. So you have this notion of a system already, that there is the interface, there is analytical reasoning, and that they fit together in some kind of a system, and we have to study this system scientifically. It has to be based on perceptual cognitive theories that embrace the dynamic interaction between cognition, perception, and action. If this is a science of analytical reasoning, it is a cognitive science by definition. But there are not a lot of theories from the experimental psychology community that embrace the dynamic interaction between cognition, perception, and action. So in fact, it calls for a new psychology to some extent. It has to provide insight into fundamental cognitive concepts. It must build basic knowledge about terms like meaning, flow, confidence, and abstraction. If you go to psychonomics or some of the psychology of vision science conference, you'll find that these are things that we don't study often because our methods are not well adapted for it. You can't do it with a t-test. It has to be more sophisticated. So I'm going to now step back a bit and take a look at the origins of cognitive science, and then I'm going to try to bring it together with a visual analytics perspective on cognitive science and a cognitive science perspective on visual analytics. The story before the story was the story of cybernetics. It started in a Hickson symposium in 1948, and these are people that you know, Wiener, McCulloch and Pitts, Ashby, Shannon, von Neumann, Turing. These people would get together at these events, and there were a number of them over many years. And the belief was that you could build a science, if you can't read the cybernetics title, but it's Norbert Wiener, controlling communication in the animal and the machine. You can find these concepts like control theory, information theory, and you can explain social sciences through these concepts. You know, people like Gregory Bateson and Margaret Mead were really thinking these concepts could help them understand society. It was one tool that could do many, many things. There's a lovely book on this, on the origins of cognitive science, by Jean-Pierre Dupuy. It's interesting. He's a philosopher, and he goes through it all in some detail. And he's also a French philosopher, so he makes his opinions very well known. It's a very sparky read. So the field of cognitive science was founded on the ashes of cybernetics. And I think that's important in understanding cognitive science today and how visual analytics might fit in with it. Cognitive science is defined by the Oxford Dictionary as a study of thought, learning, and mental organization that draws upon psychology, linguistics, philosophy, and computer modeling. Society was founded in 1979 after cybernetics was perceived to have failed. There's this sort of new cybernetics movement, but it really was a break from the old. Founders were people from all of these disciplines. I've had the good fortune to work with Zenon Polishin as a postdoc for a number of years. He was one of the founding members. They met in a hotel room in Dallas because no one wanted to fly very far, and they, got together and created this field. If you look at the people who weren't there, the key figures that weren't in Dallas were people with other names you know: Noam Chomsky, Miller, Marminsky, Alan Newell, Herb Simon, and they often worked in multiple fields. If you look at the founding members, the people who started the society, two of them have won the Jean Decaux Award, which is the award in philosophy. It's as close as philosophy will ever get to a Nobel Prize. And the three of them won Turing Awards. So it's, And in the early days, a lot of it was driven by neuroscience, but it was mostly driven by AI, the idea that we could build computer models of human cognition. And cognition, cognitive science society, all of the fields in cognitive science were supposed to drive and inform artificial intelligence. Here's this logo of the society, and instead of choosing to have a few principles that could be applied broadly, they chose to have a place, a meeting place in which these different fields could come together. They all retain their integrity. You've got psychology, anthropology, AI, and so forth. And they would come together and try to build what Paul Thagard, who was a founder and a philosopher, sort of a historian of cognitive science, calls the trading zone, after Peter Gallison's use of the term. So it's a place we can trade what we know about mind. So if you think about cognitive science, I sometimes describe myself as a cognitive scientist, and that's because I've moved between multiple fields in this group, and it's hard for me to call myself any one. But in fact, if you call yourself a cognitive scientist, it's like saying you're a native speaker of Esperanto. It really is a second language. People are philosophers and they're cognitive scientists as a second language. So if visual analytics is the science of analytical reasoning, then I think we're already cognitive science. So I want to take a look at this from a deeper perspective and ask the question of, all right, if we're not going to come up with a few principles that apply broadly, what is it that happens in that maze? What you'd like for a simple world is for these to be decomposable problems, and the philosophers come in with their piece, the psychologists and neuroscientists, and they click them all together, and we understand the mind. And that wasn't likely to happen. Paul Thaggart, as I mentioned, called it a trading zone, and that's after Peter Gallison's studies in science and technology studies on physicists. Gallison found that there was this interplay between those who work with cloud chambers and those who did modeling, and they needed a trading zone to work. Thaggart's chapter is in this lovely book, Interdisciplinary Collaboration, which I highly recommend. So the first thing that really came out of cognitive science and defined it for some time is sort of the classic model of mind. And probably the single book that typifies it most is Alan Newell's Unified Theory of Cognition. Newell came up with a SOAR cognitive architecture. And what he tried to do, which is what AI tried to do early on, is to come up with a few principles by which minds could be organized. And he thought that by instantiating these computationally, he could demonstrate that things like chunking, procedural learning could enable him to predict, to his model to fit human performance in a number of different areas. So in this book, the first third of it is brilliant, and then there's this laundry list of things that SOAR can do. And it turns out the same model can do many, many things. It's sort of general intelligence, general problem solver. Of course, AI would have none of this, and so they've long since left the building. If you go to CogSci, there's the SOAR people and the ACTAR people who try to do these general cognitive architectures, but everyone's working on very specific expert systems, and really the AI as the goal of cognitive science is just not going to happen. They've moved out. But Newell made this very bold claim that we can no longer have the idea that a theory is something you can tell somebody. A theory is going to be something computational. It's going to be a model. It makes strong predictions. And so when he says unified theories of cognition, he didn't say unified models. His models were theories. They should explain a range of behavior, these point solutions that the AI folks come up with, a program that can play chess but can do nothing else, he thinks will not advance our understanding of mind. And there's this other lovely paper he has said, he wrote, you can't play 20 questions with nature and expect to win. And from this, he's arguing that you will never aggregate statistically significant differences that are done in psychology studies to the point where you would understand the mind. You know, you're playing 20 questions, and the answer is much more complex than you could ever hill climb your way to with these significant differences. So that's a very useful perspective and a useful book, and it's the traditional perspective. Fodor had another book, Modularity of Mind. Brunswick had a very deconstructivist view of psychology. If this was my course in visual analytics cognition, we would spend some time with Brunswick. It's a model that it's still considered one of the 100 most influential books, but nobody really reads it anymore. It's not part of mainstream psychology, but it's very useful when you begin to look at these interfaces. One of the things that happens when you try to build a new cognitive science of analytical reasoning with the interactive visual interface, and you have an actual customer in the room, someone who's got a specific problem to solve, is some of the things that weren't that important in your psychology class turn out to be very useful to you. So this is a slide from Newell's book. And what he argued is you can take a look, there's some divisions between human cognitive processing that are really important to understand. At these low levels, you've got of time, so things that take place at a second or less. You've got these very simple unit tasks that's pretty closely tied to the neural architecture. You don't plan what you're going to do over the next half second. It's something that is pretty much data-driven or driven by the structure of their brain. And then you've got this task level. And that's where he really wanted to concentrate with SOAR, and ACTAR concentrates on, is really how people think, solve problems, etc. And then at a higher level, over a much longer time span, there's social interaction. You get together, you collaborate, you build a culture, and that can be many, many years, or it can be people in a room developing common ground. And I'll foreshadow a bit, emergency operations personnel that would include cops, firefighters, the people running the EOC, and the folks restoring services and the health people. Another interesting division was added later by Zenon Polishin, my old mentor. And what he said is, well, somewhere in this stretch here, there's, and it happens elsewhere, but it is always true for things that happen in that lower level cognitive proximal mechanisms category. These operations, because they're so tied to the hardware, are cognitively impenetrable. And what he means by that is what you know, think is true, expect to do, is not going to influence the way your eyes work, the way your ears hear, the way your spatial attention allocates in a busy environment. There's a lot of these low-level mechanisms that are going to be very much data-driven, and you have no insight into them. And that's what I'm going to try to convince you of in the first third of the talk. We build these new environments, and we feed them into old brains. And if you look at the Moore's Law will tell you that transistor density doubles every 24 months. There's a lot of varieties of Moore's Law, of, whatever terms you want, because they all correlate. This density is a bit faster. Its Moore's constant would be 12 months. Brain's volume has a much larger Moore's constant if you look at the evolutionary past. So you're really pretty much stuck with what you've got. Now, for these operations that take place when you are interacting in a very fluent manner, in a rich visual scene, the kind of cognition that happens when you play handball, your intuitions about those low-level processes are about as accurate as your intuitions of liver function. And so you can ask people how their liver works, and they might even tell you, but you'd be better off not basing any drug research on it. You really do have to go to the lab. So here's a lab example. We got a bit of money from Hughes, HRL, to take a look at air traffic control. And this work was the experimental psychology papers in 2005. We started the work in, I think, 1999 was our first publication in InfoVis. There was a belief that the plan view air traffic control was not going to scale. At the time, it was called free flight protocol, where they would allow the pilots to have a bit more autonomy, and they were going to rework the controller's workstation. It's important to realize what a controller's workstation does. It's absolutely nothing. Air traffic control is still largely picking up the phone and telling the people in the planes what to do. Now, of course, the reason we have air traffic control systems is to change either from one lens, change what the controller knows about the position and the velocity of airplanes and their conditions so that they can coordinate that action as opposed to just guessing. In another perspective, it forms a system of a human being interacting with a display. In this case, it's not such an active display in plan view, the standard air traffic control, you can think of that as a cognitive system. What they'd wanted to do was to take the radar view, and this is just a shot. I've got a movie too, but I decided not to show it, and begin to augment it. So now you've got all of these things happening in this display, and you can take the whole display and rotate it. So you can think of it as a fish tank, and you can just look at it from any angle to see whether these planes are going to get close to each other. Now there's other kind of alarms, there's other things going on, but they really wanted to let the people build this more rich interaction with the display instead of just observing it and making statements. Now, this is an interesting thing to evaluate. When do you decide to pull the plug on the current system and use a new system? The new system is good enough to start landing planes with it, because they want to roll this out and land planes with it. Do you get 100 air traffic controllers, pay them to go into your laboratory and run in air traffic control simulations while you record reaction time and all of the HCI variable, in hopes that you will validate that your design is not going to cause planes to crash? How long do you do that before you think it generalizes to all of the air traffic controllers in the world landing planes all over the world? Because you really don't want to move half of the system to this and have the other half of the system still using the standard displays. You really kind of want to move everything. Any significant airport you want to move. If you did find that there was an error, do you know whether it's a fluke or not? You'll never get a big enough N in your dependent measure. You'll never get enough measurement to be able to find an interaction, even a main effect. So studying this stuff is a real problem. Now, at this point, we've done something interesting, and this resonates with the, and I'll have a slide on this later, with this Pasteur's quadrant research, the idea that there's fundamental research that is application-driven. We need to know whether these displays are going to break human perception, and we need to know it in a laboratory test. So this is Polition's Finch theory, and what he has argued is the relationship between what you see and what you think is a non-trivial one. You have to have the ability to designate in the world things that are objects and that are interesting, and they may change their perspective. So they may change how they look, they may change what they do, they may change their internal characteristics, and you're processing it, but you have to process the same one over time before you know what it is and what it's doing. They say in developmental, human perceptual development, the first thing that a baby can recognize is mother's hairline, and the baby has to recognize that, and this just crashed my PowerPoint, didn't it? Has to recognize that this is mom. It's the same mom, even if they see her in a different, there we go, from a different perspective. And they begin to process information about it. And in the visual world now, this actually started in robotics, where they wanted a robot to be able to track multiple moving objects. It's something that can be seen as fairly fundamental to perceptual cognition. Jerry Fodor, a famous philosopher, I mentioned him earlier, said in an email exchange, "Finsts are the things that make thoughts true." But at a more pragmatic level, since we're not philosophers, we ask people to track those multiple targets. And I can run this again if you like. It's hard to, on my display, there's a circle that tells you which one you chose. Do you want to try that again? So what we do is to, those targets are the ones you want, the others are distractors. Well, it's not very intuitive. You can do it. And it's surprising that you can do it. And the number you can do differs. I did a lot of this. I could do 4 regularly. Almost everybody can do 3. As you get older, then you're beginning to lose some fins, and maybe you can only do 2. We all think we know people who can only do 1. Actually, there was a study done with Boston Celtics basketball players, and they can do 6, which probably shouldn't surprise anyone. So we put it in something like an air traffic control display, and we've made this schematic for a couple of good reasons. And you do the same thing. And I won't ask you to track again, because I don't want to spend the time on it. And then we want a function here, and not one of our 20 questions. And so what we do is we start changing some variables. These are fast. So the nice thing about this is you don't have to be an air traffic controller. We can run this in university students. We're so low on the cognitive architecture that it's something that the numbers may vary, but if you capture the functions are going to tell you something. And what the functions tell you is that it's not really surprising. The 2D is the one I showed you first, where it's just there's no context. The context actually helps. They do a little bit better. So higher performance is better accuracy. People for a slow-moving target, they can do more than 3, and it's moving very slowly. So these were a sharp group of students. Medium speed, now you're getting 2.6, which is more what you expect. If it's really fast, then there's a drop-off. So you kind of capture that function. But remember, in the air traffic control situation, they were going to rotate this solid. So they're going to move the whole fish tank. That's something that we have not evolutionarily experienced before. You're never in a position where you might be, you can picture somebody trying to hit a rabbit with a rock. There may be a bunch of bunnies running around and you want to do one, but at no point does the entire meadow start revolving. So we're going to turn up the heat on this. Now this would be madness for air traffic control. But as with our bioscience friends, where they'll feed a rat 5 grams of artificial sweetener to see if it gets cancer, we can turn up the volume on this, and then we're going to get a big enough dependent measure. We're going to get a big enough, that we can start to use our statistics, and we can see when there's interactions, and then we can go back and validate it in the system. And what you find is, I should give you your intuitions. My intuitions were that this is going to stink. Who thinks that this is going to be terrible? It makes no difference. And so your intuitions are that you can't do this task. When you're doing it, you think you're guessing. But in fact, the scene speeds, if you contrast it with the previous slide, where when I change the speed of the object motion individually, you spread those curves out very nicely. In this case, they're flat on top of each other. Now, with the scene motion, the speed of the targets is getting faster when the scene is moving too. So if you were to take a look at the retinal speed of those targets and ignore the fact that the world is moving together as sort of a conjugate motion, you've got a much higher retinal speed, but it doesn't affect you if it comes in the coordinates of the world. So if the world is well formed, you're able to track under those situations. If the world isn't well formed, and this is just our simple test of that was to project it on a surface with an angle rather than do a lot of computer graphics to save us programming time, now we begin to recover the effect again. So if you're interested in air traffic control and systems, what this tells us is we've validated this approach. It's something that the most obvious threat seems like it's not going to be a problem. If you ran a lot of these tests and spent a lot of money on different threats, you can begin to get some confidence in the system. From a perspective in experimental psychology, it's unexpected because we always assume that what happens on the retina is what gets processed. The way that this makes sense is to think of a cognitive system that bridges the human and the technology. We will accept stimuli that exceed our capability if the world that they're in supports them. If the context supports them, it's global motion to the context, we can do this kind of thing. And these, I'm going to skip a few of these because I'm spending some time. So that's the standard view of psychology, of cognitive science, if you will, with this idea of a computational model of mind and this approach that we can model an individual cognitive entity. What I've hopefully shown you in that short run-through, a much longer paper, is that for these kinds of richly interactive displays, these very rich displays that differ quite a lot from the experimental psychology displays we use when we do our studies, the conditions, the characteristics of the world are as important as the characteristic of the human. And you have to consider the two of them together. So this idea of a science of analytical reasoning facilitated by interactive visual interfaces is not just plugging psychology into computer science. It becomes a cyber psychology, if you will. So that's one perspective and one line of research. And now I'm going to shift a bit to a parallel perspective that we've seen in the Cognitive Science Society since about, actually, 1995. Ed Hutchins wrote a book that had a huge impact. What Hutchins had been funded, he's UC San Diego, he's one of my colleagues while I'm on sabbatical, so I go to his lab meetings, I talk to him a lot, we may actually do some project together. Most of his research comes in from the Navy. He looks at how people navigate Navy ships. And he is a sailor and can navigate. He can do distance sailing, has done distance sailing. I don't think he does it anymore. So he's a very good navigator. And that was before he's an older fellow. He was doing it before there was GPS to make it easy. With his book, he looks at Navy ships and canoes. And when people, Micronesian canoe navigators, Hawaiians, Tahitians, and the original people could, paddle a boat from Tahiti to Maui. In fact, Maui is named after the navigator. The fellow who developed this method's name was Maui. They named the island after him. It's not the other way around. And they do it with no compass, with no charts. They do it by having a mental model that is rich enough that they can make the canoe go. And it involves birds, it involves stars. Their first book on it was Gladwin's The East is a Big Bird, Navigation and Logic on Puluwat Atoll. And so this is the cognition of the head approach, but we don't do that when we have Navy ships. What they do in a Navy ship is they get a bunch of different people who have all ended up in the Navy, and they can't train them forever. And in wartime they may lose some of them, and they train them to do a set of simple tasks that all click together so that the ship as a whole is a cognitive system that navigates with people doing these operations. And the individual cognitive and motor operations that people do are very important, but they're not so complex they can't be easily learned, and you can bring a new person in, and the whole system is quite robust. So he said on this big Navy ship he was working on, there were two people who actually knew how to navigate. One was the pilot, who was the guy running the whole show, who was mostly off deck, because the ship navigates itself, unless you're in protected water, and then you pay a lot of attention. And him, because he was a sailor. And so his challenge to the cognitive science community is, all right, you want to talk about the mind as a computer. This is great for Micronesian canoe navigators. It doesn't work so well for Navy ships. If we're going to understand cognition in these complex organizations, we have to take a systems approach that looks at multi-agent interaction. So with those two tools, my lab has looked at emergency management work, and DHS is funding some of that. I have work from the Canadian government that complements it. And this takes a cognition in the wild perspective very strongly. We look at mobile analytics, sensor analytics, so first responders, situation commanders in the field with a palm-top kind of display or an iPad flavor display. Virtual EOC, advanced interactive emergency operations center with touch screens and all of this stuff. If you've seen the precision information environments that Joe Keelman talked about, you can see someone's mock-up of what that might look like. That's not, we're not researching it, that's more of a movie. A lot of work with Boeing on aircraft safety and reliability. A couple new projects. One that was alluded to, my collaborator, Vicky Lemieux, in that talk from the lawyer on economics and finance. The systemic risk analysis is quite interesting. This is the Office of Financial Research and Treasury trying to understand how we can understand the risk to an economic system, not just to our portfolio stocks. And then the healthcare monitoring and management stuff that I'll talk about briefly. So the kind of research it is, you've seen this slide before. It's use-inspired fundamental research. We also do some application-centered stuff, but what we want to do is to offload as much of the system development as we can to companies or to universities like Purdue that have big engineering programs that are going to do that kind of thing. We really don't want to build a lot. We want to design things, but mostly we want to be the organization that translates between the way the users operate, how they live their lives, and the technology design and evaluation. And then to pull back from this research questions that we can study in the laboratory to find these threats and determine how we can avoid them. Well, if we take a distributed cognition point of view on this, and then we ask, well, how is this going to impact the design of systems? Well, there's a couple ways. As we flesh out our understanding of these communities, we can give a new perspective on designing. It's useful to just give somebody a description of how emergency management actually works in the world and what people look at and how they do their jobs and their situations, and they're just going to make a better design. So there's something valuable in doing that. And if you look at the bits of CHI that tend to do ethnography, that's really what they do and frequently where they stop. They will inform you of what, these models and methods, and it does produce better design, so it's nothing to shake a stick at. What we try to do is to go further than that and to develop new, more targeted theories and methods. So we really are trying to build a cyber psychology, if you will, that focuses on the kinds of questions, the kinds of situations that come out of these field studies. If you look at the NIH roadmap, they do a very good job of this. What they've done is to make translational research really central to how they're looking at the next 10 years. There are people, there's journals of translational medicine, there are whole careers of people who just bridge between clinical application, as emergency management, if you will, and the laboratory, as well as between the laboratory and the clinic. So it's all well and good to get scientific innovation into how patients are treated, but it's equally valuable to pull knowledge from the community of physicians who actually see the patients and then formulate research questions for the laboratory. Well, and now we go, well, what happens with these two missions clashing? So we've got a decog model and we've got a mind as computer model. How do these work together? If you're an applied researcher, you can use whatever tools seem appropriate for the job. And that's what I do. I'm completely ecumenical. If it's something a SOAR model will help, I'm a SOAR guy. If it's something that requires me to be ethnographic, that's fine. The interesting thing is in cognitive science, it's tolerated it quite well. It's really hard to throw anybody out of cognitive science because we're so poorly organized that there's just nobody who knows how to do it. I mean, you'd have to get education, linguistics, and neuroscience to all agree to throw you out. It also makes it very difficult to come to a conclusion. And this is my perspective as a member of the society for 20 years. When AI left the building, we kind of lost our purpose. We're still having fun. We're getting together, and I will go every year, but we don't have that mission anymore. There's incremental steps we're making towards understanding the mind in a sort of abstract fashion. It's not something that gets you up in the morning. And what I've suggested at CogSci conferences and in their publications is, well, maybe a new mission might be something like visual analytics. Can we build, instead of building technologies that simulate the human mind, can we build technologies that augment the human mind? And now suddenly all of these people can begin to do research. How we might go about doing that, we've already decided that the division of labor model is not going to work for many applications. We're taking a sort of trading zone perspective to begin to put things together. Here I'm going to introduce somebody else from the world of science and technology studies. I'm borrowing heavily from a field of STS. These are people who study how scientists actually work and how technology is actually used in an organization from usually a social sciences point of view, but not always, sometimes a philosophy of science. Pickering looked at physicists, and what he said happens is not what we were taught. And STS is sort of based on finding things that aren't the way you thought they would be. We have this idea that there's high-level theorists, and the high-level theorists come up with deep theories, Einstein deciding this is how the world works. The universe works. And then there are sort of lower-level technology people that build the apparatus to measure the Michelson-Morley experiment or something, and they're kind of engineering, widgety guys, and they test the big theories. In fact, what he finds when he looks at the way physics works is that it is, he calls it the mangle of practice. In the UK, I probably don't need this slide, but when I introduce the mangle of practice, maybe I do now, because these mangles, I know it's still in the lexicon. Pickering's mangle was this machine for drying clothes. You throw all the clothes in, you turn the handle, and they come out as one big mass of clothes. They're not separated anymore. I don't know why he had that metaphor, but I have to explain it every time. And so his idea was you develop the technology, you have the theory, and you develop the technology, and the technology can't measure what you need to measure for that theory, and so you change your theory so it can be measured by the technology. And what it ends up happening is the researcher comes in, and here's how the world's going to work, please measure this for me. The technology comes back, and it resists. And so the researcher accommodates. What he talks about is this dance of resistance and accommodation. I put that slide in after I presented this at Boeing Company, and I put the mangle of Boeing, and they didn't like that. So I had to put that slide in. So the mangle of visual analytics research might look something like this. And this is my reinvention of cognitive science actually as a whole, or at least a substantial hunk of it. We get these people who do challenging cognitive tasks. We do what Ed Hutchins showed us how to do, this cognition in the wild. And so from this rich experience with the end users, the clients, whatever, we pull back information that goes to how we build our visualizations, the sort of nuts and bolts that Cicada does and that vaccine does, the technology developers in vaccine. We also advance social sciences methods, and I'll be talking more about that this afternoon. We advance cognitive perceptual sciences methods, and I gave you one example. I have a bunch of examples. And we also are going to change our design models. And I don't have software engineering in there, but it belongs somewhere. What you want to have happen, and what people in cognitive science say happened with cognitive science, is it's not that visual analytics is going to have a broad literature that impacts everything. The Cognitive Science Society has 2 journals. They're great journals. What Cognitive Science Society has done is to change the psychology journal, so they're more accepting of these kinds of things. So you want to get the fields to spin by themselves, and then you're beginning to build a cyber psychology or something of the sort. And I wanted to conclude this section with one of the Doug Engelbart quotes. I'm sort of a Doug Engelbart fan. I met him, and we were part of a discussion group that met online for some time. And back in 1965, he said it. He's still around. He's in his mid-80s now. So I'm going to ask for a couple questions, and then because time is likely to be a problem, I may get at least a start on the second half of the talk.
Okay, I have to ask this before anybody else. What is with the leave blank square? I've been thinking about it all presentation, and the only reason we left it in is so we can comment on it. What is it about?
It's a deep mystery that we're
I mean, you haven't worked it out yet. Everyone else knows.
You're not supposed to mention it.
Tinny, we're recording Brian. We're also recording his slides, and we're doing picture-in-picture, and that's where his picture is going to appear on the final video.
Oh, that's boring. I was thinking it was going to be some sort of, I left it in so I can give you a cognitive science explanation. I'm bored.
So now we get to just put on the video, there'll be the explanation. But we don't actually leave blank on the video, so yeah, everyone just thinks we're crazy.
So we'll cut this bit. This is meta conversation.
Can I go back to the USL experiment? So you've got some air traffic controllers monitoring airspace, and then you've got some lab experiments suggesting that people are capable of monitoring 2, 3, 4 objects. How does that relate to what air traffic controllers do? So how many objects do air traffic controllers monitor? Is it 2, 3, 4? Is it 7, 8, 9?
Each controller does a small, it depends on whether you're in a regional controller, whether you're a protected air zone controller. We always think of controllers as in the controllers who run your airport because they're the ones you see, but they're regional controllers in different places that look at traffic as it's moving across the continent. Their job is not quite as intense. They're a bit of a different beast. Planes come from all different angles for them. I mean, there's all sorts of flight paths between it. So in many ways, it's a more complex space in that sense. And pretty much everybody who's going in your protected air zone to an airport is headed for a runway. If a plane shows up that has other business, they will chase it off. They really do want it to be focused on the runways. We did some interviews with air traffic controllers. We're working with HRL. Which was Hughes and then became Hughes Raytheon Labs as a Raytheon Canada facility in Richmond Airport, and so we were talking with those guys. They're an interesting personality type. They are extremely independent. They make police seem like lemmings. So they have to have this supreme confidence in their abilities because they're directing pressurized metal cylinders full of people moving at high speeds in the air, and so you have to have a lot of confidence. They believe that they have attentional capabilities that you don't have. They will tell you that they are aware of everything happening in the world. I don't believe that's true because these are low-level bottlenecks, but I don't want to tell them that it's not true. I want them to maintain this belief that they can do their job. What they will do is have a set of planes coming in. One of the best sources for is the ethnography of the controllers. We didn't get nearly as much time as she did. Wendy Mackay, who is at, I think, INRIA, has done some very nice work on, she actually got into the control, and was able to do observation and videotape them in France. There's a small number of planes that you pay attention to. When you pass them over, they traditionally would pass over a paper flight strip, and the flight strip would be positioned in a way so it was cocked at an angle, and you knew that a cocked strip meant that there was something interesting about that plane. What you needed to remember was this is the plane that is low on fuel, it's coming in after a long flight, and the pilot's English isn't so good. And so that's one I need to pay attention to. When you read the transcripts of accidents that happen, and some of this is the work with Boeing, when airplanes have either crashed or there's been near misses, there's often a situation that may have a cultural aspect. There was a Korean jetliner that crashed in New York many years ago, and a big part of it was that the pilot was low on fuel and was unable to intrude in the New Yorkers. The New Yorkers was saying, you wait, I'm dealing with other people. And what he needed to say and was unable to say was, hey, buddy, I don't have any fuel. You'll land me now. And he wasn't able to do that. So there's they keep track of a small number of planes. They have to make sure that they understand the characteristics of an individual plane because that's very important. And I think this is a Gary Klein story. from an analysis. It may not be, but I believe it is. In the U.S., the first Iraqi war, the Vicente shot down a civilian jetliner. And what happened was characteristics of two planes were mapped onto each other. And so this was a Finst failure, if you believe the Finst hypothesis. And what happened is a plane was coming down, and it was coming down to a landing, so its attitude was a plane that's descending. It could be landing, or it could be on an attack run, and another plane was actually headed to fly over them, but it was going up, and so it was not a threat. And when you see that plane going up over you, not a threat, down someplace else, not a threat. If you think going down over you, then that is a threat. And so they had a chance to look at it, and they made a mistake, and they shot it down, because this was a very robust kind of hypothesis confirmation thing. You want to build systems that know about that and prevent that as best you can, and not rely on the humans to always make the right decision under extreme pressure. And this fits the air traffic control work, but it also it certainly fits the emergency management work.
And the Iraqi plane didn't respond to the ship because it didn't believe that the ship should be speaking to it.
Well, they must have called it and not gotten a response. I read it a long time ago. I was interested in the psychophysics, not necessarily in the whole.
Can I just confirm back to that example, what you said when you went through that slide there, that there was very little difference between the 3D rotating view performance than there was from the strict 2D.
Yeah.
Is that what you said?
Yes, and there's two things you would expect from that. One is that your intuitions about how the back half of your brain works are not very good, and when you put people in a rich visual environment, you can't just ask them. You gotta. This is what you have. You're talking liver function. You got to do some kind of science. So that's the primary message. The second one is that as you begin to inquire about perception and performance in these displays, as the displays get rich and interactive and graphically mobile, you find that people can either, and I didn't show these because I thought I'd be out of time. It actually turns out I did pretty well time-wise. They will either be detrimentally affected, and I've got some work with computer-aided design with General Motors and Boeing. Things that if small interface changes can hurt performance in ways that you wouldn't imagine. People respond to them very differently, so one person will be able to work very well. The work with GM was looking at depth perception, computer-aided design in cars in VR, so they would build things in VR. What they find is the GM designers can see it correctly, they can make design decisions, they know what the shape of the car is, everything is correct. Some of the executives that are actually making the design decisions can't see VR right. So what makes it possible for you to see VR right? Why do some people see it correctly and some people didn't? It becomes very complex to see when this stuff is going to hurt you. It differs between individuals, and the factors that actually hurt your performance are factors that are often not something you would predict. So you have to run these kinds of tests. On the other hand, what this showed us is that there's these capabilities that you have. The computer can augment your ability to track high-speed moving targets if it maintains the spatial structure of the world. If it can do that for you, you wouldn't have thought it would help. If you have a retinotopic view of the world, it's not going to help. We can augment your capability to do this task with the correct design of computer displays. So we can help you or we can hurt you, and I will show you just I don't know how many of you have a good basis of statistics. I didn't show this because I don't want to explain about the statistics behind it. I'll just show graphs because this is hopefully an answer or at least an example. So this is one of our studies. We ran it all within subject. So if you don't like big tables of p-values, you don't want to look at this. we change the display in ways that are a model of neuroscience called the two visual systems predicts how you will behave based upon certain kinds of stimuli. It's a prediction that's pretty counterintuitive. So if I put up a target in the world, it's a computer-aided design. I've got things in front of the target that are off-center. So I'm asking you to acquire this thing. So you're supposed to, put a mouse on it, or in this case, a laser pointer because it's VR. So you point at it with a pointing device, and we've got something that is in front of it and off to the side, sort of a rod and frame illusion. And I ask you to tell me where it is, and then I ask you to point to it, and then I introduce some HCI variables of giving you a visual feedback and giving you and delaying that visual feedback. What you find is that showing you, how do I put this? If I ask you where an object is, I get an illusion overall. If I give you motor control, a laser pen, I don't get the illusion. If I now ask you to give you, if I now give you a cursor for that laser pen, it gives you, it hurts your performance. A visual feedback hurts performance. And if I lag the feedback, it helps performance. So that's all counterintuitive. And I wasn't going to show these slides, so I'm not going to run through the study. What I would like you to take from this is, if you look at these p-values, individuals differ dramatically. I've got no, 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 yes, 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 whether they get the effect or not. But these p-values are either 0.8, which means there's absolutely no effect, or it's 0.001, which means there's a profound effect. The same exact situation is going to have a very different effect with two individuals. And when I change these situations, I make the effect disappear and reappear and disappear again with things like a little bit of lag or visual feedback. You would not even think to look for this if you didn't understand the neuroscience, and there is no global solution for an individual, for the population. I can't build an interface that works for everybody. I can only build an interface that works for you. So now you begin to think of this need to customize for the individual differences in some of the low-level perceptual characteristics. I don't know whether that was valuable or not, but...
I do have another question. It's about the Boston Celtic players.
Yeah.
You said that they can track 6. Now, the question I have is that, and I don't know if you have an answer, is that are they Boston Celtic players because they can track 6, or by being Boston Celtic players, they have learned to track 6?
This is something that we are actively investigating, and that is the $64,000 question. One model is it's a filter, and all the kids playing basketball. You were the best kid on this playground, and so you got a scholarship, and you did well, and you got in the NBA, and you're making all this money, and that it's you trained a lot, but it was an innate capability that you had, and having that extra finst made all the difference. In the other, view is you just practiced a lot. When I look at these patterns of performance for an individual, this mapped on, and General Motors was quite happy with it because they would say the people who became computer-aided design gurus and got their engineering degree and ended up working for us were the people who were all knows. People who all knows have no problem with virtual environments, and they don't understand why some people do. The people that end up as executives flunked out of engineering class and ended up with all yes. And so those two views of the same interface are really quite different. Do we assume it's selection and just say you're hopeless? I've got to design an interface for you, or do we look at perceptual training? Is there a way in which we can train people to have this capability? There was a study.
Depend on the task itself, like in the fighter pilot selection and training. There's a lot of fighter pilots who have aptitude. I mean, there are aptitude selection tests, and many of them don't make it through, but there's only a small percentage that get through.
Yeah.
And a lot of it is not about their ability to fly the aeroplane. Many can, and many can track while flying.
Yeah.
It's their mindset that says, look, I'm going to kill that guy in the other aeroplane that beats them and gets them through to flight school.
We know that if you bring people in who don't play video games, and I will get this, Keelman will love this slide, so I had to put it up. If you take a look at people who have succeeded in some of these kinds of difficult perceptual tasks, they can't tell you how they do it, and they can't tell you how they've learned it. You don't get any input from them. This is a lovely study by Herb Biederman on chicken sexing, and it's difficult perceptual tasks. Someone takes a look at a chicken, they pick it up, look at it from upside down, and they say, they can tell you whether it's male or female. The male chickens are drowned. The female chickens are left to become chickens, and we eat them later, but they have a brief chicken life. The way you learn how to do that, to go to chicken sexing school, is to come in and stand next to a chicken sexer. And they show you the nether end of a chicken, day-old chick, and say male, female, female, male. And you just watch, dumbfounded, not able to figure out what's going on. After a while, just by seeing those examples, you begin to be able to do it. And so they begin to ask you to do it, and they confirm it. And once you get to the criterion level, then you graduate. So they didn't know what they did or how they did it. They couldn't tell you, of course. But by observing them do it, you learn how to do it, and you can't tell other people either. And so Biederman did a lovely study of this. This is going to be a bit of a break. So I sort of did the high theory in the morning, and I'm going to do a bit more of the practical applications. But, of course, something theoretical is going to emerge from it, or methodological is going to emerge from it. So as you probably figured out already, I'm trying to avoid the applied science model that says that someone else does the research and you do the application, and instead try to move between research and application, pulling research questions, bringing them into the laboratory, pulling them out again, and then your methods advance and interesting things happen. So I have this little sort of desiderata, which you'd love to have, is instead of the abstract search for mind driving your field, have some practical instantiation of cases where people do clever things in the world. And then based on that, you can study it from different perspectives. And much of that work goes into the laboratory. Some of it will be in the field. And then you find yourself with a science that's useful, as well as, I think, being interesting. And when I say we, I should introduce my lab at this point, because I'm talking about research that these people are doing. The first three are postdocs. Natalie is working now entirely in the private sector, and I write these collaborative grants, or she writes them and I sign them, that help to get some supplementary government support. So she's really completely out there doing stuff with Defense Canada and doing stuff with companies, and so she's sort of our secret agent. Dr. Arias Hernandez runs my lab. When I'm on sabbatical, he's the guy that makes everything happen. God bless him. And so he's paid. Dr. Linda Castor is actually my wife, so I can't pay her on a grant, but she still helps out. And I'll talk a little bit about some of her work as well. And then the rest are PhD students, with the exception of Amanda, current PhD students. Amanda's an MSc student who just jumped ship for Tableau, but I told her instead of leaving, she should do a master's at Tableau. So she's going to do her master's there, and we put Jacques on our committee. So, we're trying to do work where we can have people in an industry setting, but still get their master's. Aaron will get his PhD working for an airline that I can't name, doing maintenance scheduling, and he's got a text analysis, linguistic analysis. So it's an interesting lab, social cognition and interactive expertise in natural and computational environment. I should introduce you to the lab mascot. I will do science to it. So where things usually begin is with a student analyst. When we started working with a Boeing company, we've got to date, I think, $5 million in funding from Boeing, matched it with government funding. It's a big project. It's been going on for 4 years now, and some of that 5 million will continue on for the next few years. We have students, we get them on analytical tasks, they become an analyst really before they do any research. You can't build systems for analysis if you don't know what analysis is like. So the first thing I did when I got my emergency operations grant is to pay these guys to go and address the VASS challenge before they did some work in the lab. So they get some exposure to these kinds of things. So we've got our own Visual Analytics Summer School. We now have a certificate program. We got the Andrew Wade Challenge, they call it. So they first become analysts. We've got some educational programs we're building. What we have now is the Applied Visual Analyst, in which we bring students in from any department on campus, getting a master's degree or a PhD, and they can get a certificate, graduate certificate they call it, stamped on top of their diploma, their degree in resource and environmental management, in public health, in business, and anything with an master's program. And then from that becomes the place where we recruit analytic designers who may build the technology and researchers. So we have a bit of a sort of a waterfall model. People start with the Andrew Wade Challenge, and these are some examples of challenge questions that we present to them. It's done during the school year. We've got a bunch of machines with Starlight and Inspire and of course Tableau and other software packages that we find, and we present problems. Dave Darville runs them through. He's a doctorate, PhD human factors guy, and this is a place that we do some recruiting as well. So one of the things we wanted to do was to take a distributed cognition perspective on things. And distributed cognition perspective says that we look at human and technology and how cognition is distributed between them, but also humans and humans in a technology-rich environment. So it's, again, the Ed Hutchins model of cognition in the wild, the Navy ship, not the canoe. And in order to do that, we began by doing ethnography, and I'll show some ethnographic examples, but the meat of the method we're using now is to create artificially a social situation in which people will coordinate meaning. By doing this, we hope that we can do several things. The first thing that we do that's obvious for anyone who's done a protocol analysis, when you ask people to think aloud, they tell you a story. It's really hard to get people to think aloud. Not a very good story, because when they're really thinking, they shut up. They can't think and talk at the same time. So doing protocol analysis, which I've done a lot of protocol analysis, is this frustrating exercise. And if you read, Erickson and Simon, they talk about this. Can you please think aloud? And they're doing their task, and they're saying, I need to open this file, I need to go over here, and then they sort of peter off, and you go, can you please think aloud? So what we wanted to do is to get a richer protocol, but we also want to create a situation in which participants are negotiating meaning. They're communicating about something to effectively teach each other, and then we want to see how people coordinate meaning in a technology-rich environment. And that'll make more sense when I talk about the Clark's model of joint activity theory and how we're advancing that. But that's really where we want to go. What we've done in order to make that happen is to create something we call pair analytics. If you know extreme programming, it's pair programming. I started that with a student, Jonathan Silido, when he was looking at software development. And so we were actually working with pair programming teams from extreme programming, agile methods, and analyzing their discourse that came to us naturally. What we've done is mapping that onto pair analytics. We have a student, and the student is a visual analyst, we call them, or a VAE, visual analytics expert. That means they know how to use the tool, and some people still refer to them as a tool expert. I don't like the term tool expert because they have to take responsibility for the analysis. They're the ones that have to understand when a visual display is going to misinform, when you've left something out in Tableau, you've culled some data and you don't realize that unless you've worked a lot with Tableau. They have to own that process of the analytic underpinnings. They don't know the content area, and so they aren't able to, in this aircraft safety analysis, say a lot about, airplanes and what makes them safe. There was this lovely situation where we were doing an analysis and tracking things, and they found, and I think it was, I probably will get this wrong, one of the planes had twice as many engine failures as some of the other planes. This came out, and we thought, there's a smoking gun, twice as many engine fail. And one of the Boeing guys looked over, and they were explaining this and go, "Oh, that's a 4-engine plane," and walks away. But they have to master the analytics that underlies the analysis. They have to understand things about confirmation bias. So they have to be really application-aware cognitive scientists, we can say that. How we do that training is a work in progress. I've got a graduate seminar in analytic cognition, and I teach some problem solving. I teach heuristics and biases. I teach, a bit of perception. It's really, there's not a textbook for this stuff. But that visual analytics expert, as in pair programming, the least experienced programmer owns the keyboard. The most experienced programmer steps back and directs it. And through their communication, the agile people will tell you, the extreme people, programming people will tell you, that communication means that they're going to do things clearly, the software will be easier to understand, and also the junior programmer learns. What we've done is to do the same thing with a Boeing safety analyst. That's Roger Nicholson, who's a senior safety analyst at Boeing. Instructs us in how to understand aircraft safety. Our student, VAE, runs the software. It explains the visualization. So you can watch them sort of understand how to work together and capture that. And great things come out of these protocols. And of course, we video this session and we capture the screen. And I put a CogSci references. We have some other references. We've done, I don't know how many of these things for Boeing. They've funded, we do a lot of them in the context of student internships. They've done at least 16 internships with my lab. Not everything has a product out of it, but the one that we did first, and it was, I think, quite successful, looks at these incidents. I don't know how well you'll see that. That arrow is a birdie. And you see little bits of flame coming out of the back, which lets you know what happened. And so if this, I will probably interrupt this because the plane lands safely and all's well. There was a famous incident in New York where the birds flew into both engines, and that's more of an issue. And so this is not that uncommon. And you get these lovely pictures of various bird parts. It's amazing what a bird can do to a plane that's flying 300 miles an hour. Canada geese, our country's national bird, are the most effective at bringing down airplanes because they're big, heavy birds and they like to hang out together. And they're too dumb to get out of the way.
The bird ripped that piece of wing pelling through right there. That space.
Yeah?
The bird ripped that metal.
Yeah, the bird went that far. The bird will be all right, though. It got medical treatment. No birds were harmed in the making of this movie. Anyway, here's some. I like the bits with the legs sticking out. These little bird and plane shots. And so what we did is we got Andrew Wade, who was our first star student, and he got him together with Roger Nicholson, and they presented at bird strike conferences. There are bird strike
National Wildlife Strike
conferences
and uploaded into the visual analytics tool Tableau. The initial view shows all of our dimensions from the data set in this window here. Dimensions include things like the airport, aircraft type, damage to the plane, incident date, and operator. Measures are also extracted and include numerical fields in the data like height and speed. The main window in Tableau contains shelves such as columns, rows, filters, color, and size. Tableau employs an interactive drag and drop interface where you can select dimensions and measures and drop them on the shelf. One of the things we wanted to visualize was the kinetic energy of bird strikes. In many cases, the National Wildlife Strike Database contains the speed of the aircraft and the species of the birds struck. Using a species lookup table for the average weight of birds, an approximate value for kinetic energy of the strike could be calculated using Tableau's calculated fields. In order to visualize kinetic energy in a useful way, we mapped it onto the flight envelope. Tableau also has the ability to suggest visualizations for your data based on the data type, saving some of the initial work. Selecting the field of height and the field of speed and clicking Show Me results in a suggestion to use a scatter plot. Once we tell Tableau to treat height and speed as dimensions, we are presented with a visualization of strikes in the flight envelope. Speed of the airplane is shown along the x-axis and height along the y, with each individual dot representing a single bird strike. We can immediately infer where in the air and at what speed strikes are occurring from the visualization. Dropping the calculated field of kinetic energy onto the size shelf affects the size of the dots. Here, larger dots represent more kinetic energy involved in the strike. At any time, we can mouse over one of the dots to see more information. The interaction with the visualization is part of what makes this tool so powerful. What are the high kinetic energy strikes at zero height? By mousing over the large dots, we see that they are wildlife strikes such as deer, elk, and cattle.
We did have one case of a fish strike.
For purposes of our analysis, we are interested in strikes to commercial airplanes only. Tableau allows you to create groups and sets, which we did for Boeing airplanes, Airbus airplanes, and everyone else. Once the group has been created, we used it as a filter. By simply checking the boxes we are interested in, the visualization can be updated to only show Boeing and Airbus planes. We initially utilized the color shelf for species of bird involved in the strike. Dropping species on the color shelf assigns a color to each species and then to each dot. The species are listed on the right here. However, this is
American
a bit
alligator.
so we narrowed down our search further using the FAA's Most Wanted list. Creating a group for the Most Wanted list the same way a group was created for the Boeing and Airbus planes.
Armadillo, the Texas fields there.
Dropping the Most Wanted list onto the color shelf results in a much more manageable visualization. There seems to be an abundance of one particular color dominating the display, orange. Looking at our color key on the right, we see that orange is our good friend, the Canada goose. Canada geese are large birds, and strikes with them have a significant amount of kinetic energy. This is immediately obvious from the visualization. From here, we can look at the highest speed collisions by kinetic energy just by mousing over the dots in the display. We were also interested in visualizing damage. Changing color to represent damage rather than species is as easy as dragging and dropping the field onto color. Now, dots that are red are planes that have been destroyed, pink are substantial, orange, major, turquoise are uncertain, and green have no damage. There only appears to be one plane that was destroyed, and mousing over reveals that it was the US Airways flight we are all familiar with. This visualization allows us to begin with the most damaging strikes and get a sense of where they are occurring. We were asked to do this type of analysis for radome strikes that have been damaging the ILS localizer antenna. By making a quick filter for damage to the radome, we can check only those records where the radome was damaged and then see the results. Mousing over high kinetic energy radome strikes led us to find some of the most damaging strikes in just seconds, as opposed to having to read all of the individual reports. In addition to kinetic energy, we used Tableau to look at geographic distribution of strikes by species. The size of the pie chart represents the total number of strikes at that airport, and the size of the slice is the percentage of strikes from one particular species. Again, this has been filtered to the FAA's Most Wanted list. One important thing to note is that not all records in this dataset contain species and airport location, so the ratios are not always perfect. However, it's rare that we will ever have an entirely correct dataset, and this gives us a good estimation of the actual ratio. Combining geographic location with time of day, we can see the number of strikes at different points during the day. The size of the dot is representative of the total strikes of Canada geese at that airport. Each map represents a different time of day: dawn, day, dusk, and night. Here we see that there are still a significant number of strikes at night, contrary to what some flight crews believe. This visualization shows both seasonal and temporal fluctuations in number of strikes. The height of each bar shows the number of strikes in each month, and is colored by time of day. One interesting thing from this visualization is that in October, nighttime strikes actually outnumber daytime strikes, shown by the larger blue bar. This visualization could easily be filtered more, looking at specific airports, regions, or even locations of strikes on the plane. This video has shown only a few of the potential applications of this tool using the National Wildlife Strike Database. We've also played around with things like struck versus damage ratios for different parts of the plane, as well as the rate of strikes based on factors like wide body and narrow body aircraft. To sum up, the ease of interacting with data and visualizations makes this tool a powerful addition to any bird strike analysis.
The interesting thing about Tableau, it doesn't do anything that you can't do with some of the statistical packages. I mean, VASS has great graphics, JMP has great graphics. Because it has this kind of fluent interaction, it picks colors intelligently. You just drag and drop things into fields. It chooses a representation. It's a pretty good representation. You develop this kind of fluent interaction that helps this paired analytics session become something other than can you run this analysis while I get a cup of coffee? Andrew was so good with this, and Aaron were team students. We ran something where Boeing had us face their customer. So it was a customer that had issues with maintenance on a particular Boeing airplane. And we gave them a presentation of our analysis while Andrew sat there and in real time answered questions using Tableau about the data. So they would say, well, what about the maintenance scheduling for these planes that were, and he could give them, he would follow along Aaron's presentation and then answer the question using Tableau. It's just brilliant. I'm not going to do the Inspire version, I think, in its entirety because it might take too much time. I'm going to see how long this video is, but I do want to at least start it, if it will start. I think it wants me to keep my hands off of it. There we go. But you've used Inspire, so it's useful to see.
It is necessary to look at the text in the remarks field within each report. Often, in current practice, this means a lot of reading. Inspire is a tool designed to visualize unstructured text, helping to focus the analysis on the text you're interested in and lower the overall amount of reading. We used Inspire to examine pilot response to bird strikes using reports from a Boeing safety database. An example of one of these reports is shown here. It contains a remarks field, event ID, date, aircraft model, airline name, location, damage description, region, phase, and altitude. Those fields were selected from the database because they are the ones of most interest for this analysis. After importing 1,087 bird strike records into Inspire, one of the initial views is the galaxy. Here, each of our records is represented by a single dot. Documents cluster together based on similarity that is calculated from word frequencies and co-occurrences. You'll notice there are 3 words printed above some of the clusters. Those are the words that contribute most to that cluster. Just glancing at the words above clusters gives you an idea of what's going on in your data set and the language being used. I'll remind you that we haven't actually read any documents yet, but we've already learned something. The theme view in Inspire shows clusters on a terrain map, using height to represent more documents within a cluster. Because of our powerful visual system, we can easily identify the highest peaks, and therefore the densest clusters. This tool will not, and does not claim to, remove the human from the analysis. Interaction with Inspire is key, and there's a significant amount of cleaning that must occur. Take, for example, the cluster with birds printed above it. We already know that all the records in the data set are about bird strikes, so this word doesn't really tell us anything. By removing birds to the outliers, Inspire will rearrange the documents based on the next most important word. As you can see, the distribution of clusters has changed, and we now have new words above the clusters. As I mentioned, we were interested in looking at pilot response, particularly when pilot response was incorrect. In order to find strikes where the pilot had a chance to respond, we needed to isolate records that were detectable in flight, as opposed to later on during maintenance checks. Pilots use sensory terms to describe what they notice on a flight deck, terms like saw, heard, or smelled a bird. We began with a list of sensory words in a query, using the asterisk as a wildcard to capture different tenses of those words. This query generated 380 records out of our 1,087, using words like sound, noise, hum, stall, odor, and rumble. Those records are then highlighted in green in the galaxy. Moving the other 707 documents to the outlier bin, and then updating our view, gives us a summary of only our searched records. The word vibration occurs quite frequently, and as it turns out, is used very often when there is a bird strike. Returning to the query and adding VIBR star will capture additional documents that use words like vibrate, vibrates, vibration, etc. Querying again reveals 440 documents and added 60 from before. This iterative process of querying and interacting with the visualization continued until we were satisfied that we had most all of the detectable strikes. A similar process was carried out for types of responses such as air turnback, diversions, in-flight shutdown, and rejected takeoff. Using the groups tool, we can see that there are 138 rejected takeoffs in the data set, and 356 air turnbacks. If I select all of the rejected takeoffs, I am shown 138 out of 138. However, the power of the groups tool comes from the overlap feature. Out of the 138, I can see that 59 were detectable bird strikes, and 41 were ICAS model planes. Opening the aircraft models folder, I can see how many of each plane had an RTO. By selecting both RTO and detectable, and then clicking the overlap, I have selected only those records that were detectable strikes and RTOs. At this point, we had narrowed our search significantly, and reading the actual reports began. Assessing whether the pilot made the correct response requires a subject matter expert and analysis of the remarks field. We were then able to group together correct and incorrect responses for further analysis. Inspire has a nice highlighting feature, and will highlight words and trees in order to draw attention to the most relevant parts of the text. This tool minimized reading significantly by helping to drill down to those records that were of the highest importance. We never read all 1,087 reports, nor do we need to. This is often the case with large data sets, and improving efficiency can be aided by visual analytic tools and methods, such as those used here. The results of this analysis will help to inform flight training manuals, as well as determine whether airplanes are providing enough information for pilots to respond to strikes when they occur.
Yeah, I let him go the whole way. It was a nice story. And another commercial for Inspire. We'll sell more of those free Inspire licenses for our friends at Vienna. So the internship was a success. We had these 10 sessions, and I'll talk about the analysis of those sessions back in the lab. He changed the design in 4 airplanes and the pilot safety manual, which isn't bad for a 4-month internship for a graduate student. He was able to present the work to quite a few engineers. They have a community of practice. There was and so on. So it had a good impact on Boeing and really was instrumental in getting us the sort of continued work with Boeing. We do a lot of projects that anything on safety, we can show the data, we can talk about, and anything that is proprietary, that, you know, especially when I'm here so close to Airbus, we can talk about. But the safety stuff is good to work on because it's completely public. Aaron, the other student that I mentioned, is working on something that's proprietary, and we have issues with what he can publish and what he can't publish in his thesis. So when we take a look at these back in the lab, so the joint activity theory was, the paired analytics was useful in getting the analysis done. We got these great tapes. They have nice protocols, and we can go through and just do a protocol analysis and look at the, you know, what an expert asks and what they don't ask, and you know, just take a look at this problem-solving procedure. But we also want to understand whether we can't take some existing social sciences model, in this case a social cognition model called joint activity theory, and advance it to deal with communication in technology-rich environment. So we're going back and taking an off-the-shelf method, and then we're adapting it and modifying it to look at the kinds of situations we have. Gave you an example in my first talk of how we've changed the way we look at psychology based upon these applied questions, and now we're trying to change a bit of the social psychology as well. We started with joint activity theory, and joint activity theory is Herbert H. Clark. He has a book called Using Language, although we're interested in moving beyond language. And in it, he lays out this very comprehensive framework for how people communicate. And he does so by refuting the idea that we communicate by passing messages. His argument is that that's not a very good way to understand how people communicate, because the messages they passed are based in their understanding of what the other person is able to understand the referent to, whether they understand it as something that's shared or whether it's something that's really abstract, and they understand that that person is trying to coordinate with them. So, as a listener, my job is to give you signals, which I do unconsciously, whether I understand or don't understand. I nod, I look puzzled. As you speak, you gesture, you try to make sure that you understand this, do you not? This notion of this implicit meta-channel of handshaking about communication that we do quite naturally, which is one of the reasons it's difficult to handle video conferences, and if you do teleconferences, you have to be careful that there's not misunderstandings and so on. So what Clark says is that if you look at it, really it's a system that has two people, a cognitive system, who together coordinate their behavior. It's an essentially collaborative activity like playing a duet, as his example, or paddling a canoe. And so we work to build what he calls common ground. Common ground isn't necessarily agreement, but it is really a metacognition. It is an understanding of what that other person, how that other person will interpret your utterance, that you expect them to confirm from you once you say that thing, then that confirms for you. They confirm for you that it was understood correctly. If there's a problem, they go back and repair. So it's this cooperative kind of process that's based in your ability to build a mental model of what another person knows, thinks is true, intends to do, and what they understand. The argument is we do this unconsciously. The argument has been brought forward that it's one of the major deficits in autism is that inability to have that metacognition. And so they have to compensate with cognitive skill, something that we do automatically. So high-level, high-performing autistic people can communicate, but it's a lot of work for them, as they have to remember stuff instead of having it happen automatically. So Clark's theory doesn't just throw this out as a conceptual way of looking at communicating, but he really gives you this specific, explicit taxonomy of the kinds of processes. It's really a very in-depth, structured framework. I try to get students to read it. They don't usually make it through. Very few people have really read Clark properly. So he defines kinds of common ground. He formalizes the notion of activity as a joint action and describes its processes. And so you can define common ground as a set of things that are mutually believed by both speaker here. They don't have to agree, but they have to understand. And they have to either ground or acknowledge the understanding of another speaker's utterance. That's your job as somebody who's listening. And Clark has a number of principles. I'm only going to sample from Clark. It's a really complex book. One is the principle of closure, the idea that when you perform an action, you are going to require some feedback from the other person that they've understood. If they don't give you that feedback, then you're just going to keep explaining. And so you need to know whether that communication got through or not, that kind of handshaking. Clark talks about metacognition, these mechanisms that we use to establish metacognition, things like vocal inflections, gesture expression, hesitation, pausing phrases. If a speaker looks out and people look puzzled, they will slow down, they'll say more. They won't necessarily be able to tell you that they did it or why they did it, but they will recognize it's not getting through and they'll back up and explain, which is one of the reasons, it's one of the mechanisms you have to get rid of when you become a professor or an instructor, because you're often looking out at a sea of puzzled faces, and if you just waited for everyone to understand, you would never finish your lecture. So Clarke's theory draws upon these metaphors of joint activity. I have a little musical clip there. And it turns out Clarke is a pianist, so he's a performing musician. I include this because one of the things that Linda Castra, my wife, I mentioned her earlier, she works with us, is doing is applying Clarke's theory to how musicians negotiate meaning and performance, a field called performance science. And so Clarke uses the metaphor of music to describe language as a coordination activity. And what Linda's done is to take the language framework and move it back into music and see the mechanisms that musicians use to coordinate. They can't speak when they're playing, but they can gesture. They have ways of annotating their scores. There's a lot of techniques they use that enable them to play together very well. So what we do when we get these, it is like all of these kinds of qualitative research, video analysis. It is laborious, painstaking. You go through the video coding things that Clarke's theory tell you are salient. We began with what they call open coding, where we coded just about everything, but it was just to see whether we're missing something. We very quickly zeroed in on a Clarke centered coding. We had two coders, Richard and Linda. Both of them have PhDs. Both of them did their dissertations doing qualitative research methods, grounded theory, flavored methods, so they're skilled at doing that. We need more coders, more people to look at the same things. We need to collaborate with other groups. We're talking with Simon about it. Once we begin to trade our coding strategies, then we can really begin to get more faster out of these tapes. We have to get to the point where we can do. It doesn't take us 100 hours to look at 5 hours of collaboration. We just can't afford it. So you'll find things like markers. People say okay, all right, and that's sort of straightforward. We call those vertical markers. Horizontal markers are such as yeah and are used to signal continuation. So I understand you, keep moving. One of the interesting things that happens in these spoken communication in a technology-rich environment that doesn't happen in the kind of face-to-face conversation that Clarke has traditionally looked at is we have to manage joint attention. We're talking about stuff in the screen that reflects big, deep concepts about what's happening to these airplanes. So there's a lot of directed gesture, gaze, finger pointing. We use the mouse a lot to gesture. The student analyst, the visual analytics expert, does a lot of mouse things. Another thing that we find that's really interesting is that when you're having this kinds of a session and you're at a point where in a standard single player protocol you would stop talking because you're thinking. You don't do that when you're in this conversation. First, it would be rude to just shut up and pretend the other person isn't there, and people don't naturally do that. But second, there's this possibility that they will move on to some other subject. They're going to say something that's going to make you lose your train of thought. There's all sorts of pragmatics as well as social reasons that what you do is to keep them on the topic by thinking aloud, by talking aloud. We see these self-talk incidents. And those are gold. They're these lovely protocols where the person is talking over to communicate to someone else. So it's not just self-talk, which may have reference that we don't understand, but they choose terms because they're grounding that will make that understood to the other person. So those are wonderful protocols. You'll see this happen where they're working together, and then all of a sudden somebody moves the mouse on this and just starts giving you this stream of consciousness. And so we're really concentrating on those as something that's low-hanging fruit. So that's a quick run through of the joint activity work. A lot of our funding, and it started with DHS, and we quickly got Canadian government funding, looks at a more complex coordination problem in emergency management. So I'll talk a little bit about that before we end. Your users are bears is a quote that was given to me by a very senior police officer. We had, when Visual Analytics started, Microsoft Research got interested, George Robertson. and they had us all out. And so we were there, and they had the office product group there. The senior manager for our office, Jim Thomas, was our master of ceremonies as always. And we were, going through these kinds of possible visualizations and approaches that we could use. And we brought in the police and the fire, some emergency management people from Washington, Puget Sound area that Microsoft could bring in. At one point, this gentleman stood up looking at some mass of parallel coordinates and said, "To me, that looks like a plate of spaghetti. Your users are bears." And I remember that quote always. What we're trying to do to people who are not necessarily experienced in visualization, they are experts at what they do. And we can't de-skill them by putting them in a situation where they're not able to do their job until they understand parallel coordinates. So we've got to build systems, multi-bear systems that enable people to coordinate based on what they already know and what they can see. We're using some technologies that don't have rich visualization, small form factor devices, and so on. The way things have evolved, and this is the body contact with the user community that I'll talk about, there's a lot of interest in bringing into this cell phones. If there's an earthquake, people have got to be able to use a cell phone to find out what they can do. They want to monitor that stuff. First responders will have more dedicated technology. Blackberries, if RIM doesn't survive, they like Blackberries because they're secure and robust. We're working with the data fusion centers and command centers, and we're augmenting the command center with interactive tabletop walls, etc. Now, in order to do this, the first thing we needed was someone who could give us, and this is off-the-shelf ethnography really, but I think well done, give us entry into that community. We're not going to show up at the Emergency Operations Center in the city of Richmond and say, we're from the university, we're here to help. We've got to have someone who buys in. And that guy is Bob Poole. He's a firefighter in Mission, still active duty firefighter. He's been working with the federal government. And Sheldon Dickey, I think, put us in touch with him. But he's interested in technology. So he's our guy that gets us in the door. And so Bob set us up. My postdoc, Richard, went to the Justice Institute of BC and sat down next to the people who were training to become emergency managers. We paid for him to take all the courses. So he's fully qualified. He then trained in the city of Richmond with a new hire that they had. And so when there's an earthquake in Vancouver, he's going to be down there, manning a station. He's completely qualified, and he participates in their exercises. It's a lot of work to do this. It's something that our company is not likely to do, but it's something that we can do. We've been funded to do. We were part of the cross-border earthquake experiment, they call it, that the CREATE in Canada, ERE in the United States, and we had people at all of these stations. One of the things that we're coming to understand more and more as we actually have body contact with people in the user community is that technological solutions alone aren't going to do it. People have to build an analytics, and analytics is not the analysis, it's the underlying justification for the validity of the analysis. And logic, you apply logic to a situation, but the rules of logic are the analytics. And the rules of logic have been developed in such a way that if you start with true antecedents and you use them correctly, you get to true conclusion. We really need something that parallels that for the visualization as it's used in action. So we need to really think of the method. And these methods themselves are going to change not only the technology, but the analysts, the training of the analysts. And what we often do is by putting the student into Boeing, then we have the ability that the safety analyst doesn't have to understand how to use this technology. They're supported in that. And so we're really looking at human organization and technology as a triad. We're working on the methodology, and I see I'm running short on time as another reference, Topics in Cognitive Science, where we describe it in more detail. The last bit is a project with BC Injury Prevention. Why that's is interesting, and I'll show just a few screenshots, is it's multi-party analytics as in the Emergency Operations Center. People have to coordinate on what happens for the different sectors and move supplies from one place to another. But they're also building policy. And so they're interpreting policy and they're building policy. These are people who will sit around a table, often in a northern community, and decide how they reduce injuries to children. And there's the schools, there's the parents, there's the police force, that all have to support and agree on what they do. It's got as much of the concept mapping of this notion of a visual rhetoric as it does a data visualization. So in order to do that, we've taken the pair analytics model of a subject matter expert and a visual analytics expert, and Samar is the person in the hot seat for this. And her job is to be the analyst who can not only understand the analytics, but in a sense put on a different hat as the kind of process facilitator that you often see in businesses. They'll bring somebody in to help you make decisions and to help these people do their work and come up to a decision. I'll just briefly show the indicators to look what we're looking at. Things that include driving, car crashes, things of the sort, leisure, injuries in playgrounds, and they're children, but they can be up until 18. Bicycle helmets. But we've also got violent crime. I mean, that's a non-disease. It's an injury of a sort. Suicide. There's anti-bullying. There's the facilities. Because British Columbia is often very rural, there's situations where there's, it's volunteer fire department, there's no ambulance service, only helicopter, so there's a lot of really challenging things. We use Tableau, we build dashboards, a lot of brushing and linking. It's something that the participants would not be able to do, they're bears. But what Samar does is to do this for them and to help walk them through this. She hasn't quit yet, but it's a big challenge. And this takes us to this notion of a visual rhetoric. As we move into the policy world, inevitably analytics, and especially visual analytics, is not going to be able to stay with the data. At the end of the day, people make policies, they make decisions, and they put them into operation. We are going to extend into a world where we're no longer dealing with data, but dealing with decisions made about the capabilities of an organization. We've had a lot of briefings by people from the TLAs, the three-letter agencies, and what they will tell you is the analyst looks outward and the policymaker, the client, looks inward. The analyst tells you, what's happening in Iran, and the guy who's making the decision, Joint Chiefs of Staff or whoever, says, what are we capable of doing? The analyst isn't going to know that. What's politically possible? What's physically possible? So inevitably, and what they will tell you is that handoff is hard. It's really difficult to, they end up either, you get these questions like, give me your best guess, are we going to invade or not? Well, I don't want to do that. And so inevitably we bridge that. This is the stuff I'm working on now, the concept mapping and related methods, so that's an obvious thing. Diagrammatic reasoning, some of the visual communication standards, visualizing argumentation. There's another lovely book on just taking the group process, putting it in a visual representation to help people move towards decision making. And there's some logics underneath that, so there is some structure. There's already a possible kind of analytics. At that point, we realized we're doing business, and I found a lovely quote from some very famous guy, supposedly, Bennis and O'Toole from Harvard Business Review, in which they say, how business schools lost their way. It's a whole condemnation. And they say that they need cognitive science. So at least a few people think so. The other group that thinks so is the National Science Foundation. So they are planning for a FODAVA 2, a second $20 million project for one institution. And these are the topics that are the core topics for the white papers that we're talking about. And you can see that there is a lot of interaction. The visual discourse or visual rhetoric did make it in there as a topic area. Last bit, if you're interested in the application side of this, I encourage you to submit to our mini-track. We are not trying to duplicate VASS. VASS is great. What we're trying to do is to have a track at the Hawaii International Conference for the Systems Sciences where we really look at how this stuff works in the real world and we begin to get people from the client communities involved. There's already a really nice emergency management track there. Murray Turoff, who's a famous guy, runs it. So it's actually a good place to meet them. For some reason, a lot of people are willing, who don't normally go to academic conferences, will come to this conference. It's inexplicable. January 7th through 10th, on Maui. So, thank you very much.
When's the due date?
When's your submission date?
Yeah. Unfortunately, it's passed for this year, but we'll do it again next year. It's growing quite nicely.